so let me pull up my PowerPoint and then we'll get started. So just to summarize where we were, so we had established the looking up part of the Kalman filtering process.
Yeah.
So now we're going to finish off by getting the other two equations, which is the counting steps part, and then I'll show you a MATLAB example that I found on GitHub. I checked these equations, it seems to be the correct implementation, and then we take a look at what it's saying really. So this is the dynamic case. So this dynamic does not mean statics and dynamics, or kinematics and dynamics. This is dynamic meaning something is changing. Okay, so KF inclusion of dynamics means in our case the robot is moving, or maybe a chemical process or chemical plant, there's something that is changing. You know, you're not measuring a static chemical process. As I said, Kalman filtering can be used for many situations, not just robots or some other. And so I gave you the analogy that if you want to pursue or continue with the resistance example, it would be as if the resistance value is changing according to some kind of model, like step counting is replaced by a rough equation. So that's what it is. That the part where I say steps, right? Think of it as a rough equation, and so you need a measurement. Otherwise, you will lose everything. So that's what it is. So pose is a three-element Pose is a three-element vector in 2 dimensions. It's a 6-element vector in 3 dimensions, and you can also add velocity and so on. If you want to estimate velocity, you can also put it there. So basically, why are we doing the 1D position estimate, which is not a very interesting application? It's because you have to start simple. So a robot that only moves in 1 dimension is obviously not very useful, but we use it to get started on the process of understanding. So the Kalman filtering assumes Gaussian probability density functions for the 3 uncertain things going on. So this morning we said probability is a way to model uncertainty. So there are 3 areas. One is the robot state. So the state of the robot is never known precisely. So you use a Gaussian to model that. In our case, 1-dimensional position will be modeled by Gaussian. The motion model, the step counting, right? That's going to be modeled by a Gaussian function also. The uncertainty in it is going to be modeled by a Gaussian function. And finally, the measurement model, the fact that a measurement is not precise, that uncertainty part of it is going to be modeled by a Gaussian. So as we said earlier, the Gaussian is defined by just 2 parameters for the 1-dimensional case, similar extensions to the multi-dimensional case, mean and variance. Only these parameters, you're looking at a graph, but really it amounts to updating those 2 parameters. The graph is moving along, but it's drawn on the basis of just 2 parameters. So those are the 2 you need to update. And this is, again, the counting steps part, not the lookup, because we already dealt with that. So you end up in an optimal recursive data processing algorithm. That is the Kalman filter result. It's optimal overall, not each individual estimate, but if you use it many times, overall, that is the best rule you have. Recursive in the sense that only the previous estimate and the various Gaussian statistics. You also need the various Gaussian statistics are needed to generate a new estimate. If robot position is lost, we definitely have a problem. We cannot recover from losing the 1 position we maintain. Markov, as you'll see, no problem, because you have so many. So obviously you can't lose them all, so it get picked up. That's the point. If temporarily I feel lost, keep going, and with measurements, the true position will again rise in terms of the probability value. So in Kalman, if you lose it, you have to get a GPS reading. Otherwise you're stuck. You have to have some way of finding out where you are. Now this is an excellent conceptual figure. I don't know whether this guy came up with it or it was in some original paper. This guy meaning Siegwart. This is from the textbook of a guy called Siegwart who works in Switzerland. So we have 3 pillars, right? So what those pillars are there for is for you to say that I know the map. That's what it means. The 3 pillars means that I know a map, and he's assuming that there are 3 pillars in the environment, just to explain the process. So the 3 pillars don't mean anything else other than he knows some features in the map. Okay, So the initial position is represented by Gaussian uncertainty, right? We said that's one of the three, remember? So the initial position is represented by Gaussian uncertainty. So some action you take, meaning that you make the robot move, count steps, whatever you want to call it, and then you update this. So these equations we will, expose shortly. But the point he's making here is that Gaussian becomes a much shorter and fatter Gaussian. So that essentially is saying that if I count steps, I'm becoming less certain about the position. And what is a less certain Gaussian? It is a wider and shorter Gaussian. So that's conceptually shown by a shorter and wider Gaussian. So it's time now for a measurement update. So you look up and you see a single pillar, right?
Yeah.
And since you know the map, you say, okay, I've taken the measurement, and the measurement given the map and the location of the robot is modeled by this Gaussian function. In figure C, you have a narrower, taller Gaussian, and the reason is typically the measurement provides more certainty compared to the autometry. So this Gaussian should be sharper and narrower. Now, remember what's going on in the Bayes theorem? These two should be multiplied.
Yeah.
The top is the location from odometry, here it is, and given the measurement, where would I be? If you want, I can put back the Bayes Bayes equation. Let's do that because we need to be certain that your understanding is as it should be. So where was that? In the review of the localization connection. That's what it was.
So it was in localization and mapping and in probability.
Okay, yeah. So here it is. Tell me if this is the right document. Yeah, here it is. This is probability of L times probability of the measurement given L. Right?
Yeah.
We'll get to this soon.
Yeah.
But for now, forget about that because it does not depend on L, right? So the product of these two. So that's what we're doing. So let's see. This multiplying that produces this. But there is a hidden step. And that hidden step is a denominator. Remember I told you that it's going to be the same for all values. And so you totally determine and you divide by that.
Yeah.
So essentially, when you multiply these two and create the product, initially the area under the curve will not be 1. Because you're just multiplying two Gaussians, right? There is no reason why when you multiply two Gaussians, the area under the product Gaussian should be 1. But that intermediate step, the numerator of the Bayes rule, if you find out the area under the curve, right? And then divide every point by the area. That is the same area, right? There's only one area. So when you multiply it, initially you should get an intermediate figure. Between C and D, it is just the product. Then you find out the area under that product and then divide each point by that product and you end up with the probability again. So that's why you don't have to worry about the denominator. The probability of I is not of interest. Because by using this area normalization rule, you get the right result. So figure C is a perception and then there's more to it because figure D is apply Bayes rule. So I've repeated the figure. So apply Bayes rule to accomplish sensor fusion leads to sharper Gaussian. Look at it. You can tell, right? If you multiply this by this, you get a sharper result.
Yeah.
And then you normalize it with the area, and there it is. Now you can count steps again for a while, not forever.
Yeah.
But for a little while, you can count again. So, combining information from two independent inaccurate estimates produces a result that is better than either of them. So that's hard to believe, right? But we showed it. Remember the resistance, parallel combination of resistors? So when you combine two not so accurate estimates, you get a result that is better than the better of them. Not perfect, but better than the two. Here's the conceptualization. Now, the symbols have changed because now all of a sudden we have Q. I couldn't help it because I went to this book by Sigwart, and you have two choices. You can change the symbols of Sigwart, but then the students go to Sigwart's book, they'll be confused, what is this Q? So instead I said, yeah, the symbols are different, I'm explaining it to you. So I told them the notation is changed to match those and see what, which is reference 1. So there's one thing misleading about this, because P1Q is the steps update, right? P1Q, and he assumes that P2Q is the measurement. You know what's wrong about it? This cannot be the shorter, fatter Gaussian. The measurement cannot be the shorter, fatter Gaussian. So he has chosen a bad example, because the measurement is not worse than the econometry result. So maybe you should have interchanged these two, call this the measurement and call that the, But the main point is, once you fuse them by Bayes' rule, you end up with a dark Gaussian, and you can see there's much more certainty.
Yeah.
The point is, the odometry will be the worst Gaussian. It's not the measurement. And then we did this earlier, right? We said that you can combine the two. You can write it in two ways, remember?
Yeah.
Now, why this equation may look different from the Kalman update equation? It's the same thing, because here is the Kalman game. And if you don't like writing it like that, you can expand it and write it as Q1 times this plus Q2 times this. This is what I said, like a little bit of this and a little bit of that, right? So, this plus this is equal to 1. Again, this plus this is equal to 1. So this is a fraction of 1, and that is the remaining fraction of 1, right? So it makes perfect sense that the Kalman rule tells you something that is intuitive. You know that this makes sense. Alright, so now what are we doing here? So we brought back the perception update, remember the same thing? But now I'm writing it in terms of the new symbols. So KK plus 1 is the Kalman gain. Now pay attention, because I dropped 0. Because 0 is the very first estimate. I'm not just going to do it once and get x1 and say, okay, I'm closing shop. I'm going to do it repeatedly. So I need an equation which is general, right? So that's what I'm doing here. You see here, from K, I go to K plus 1. That makes sense. It's just one step. And then when I do that, K plus 1 becomes the new K.
Older K.
Right, and then you keep on going. So it's not good to bring 0 into it, because 0 is the very first estimate, and you do it only once. So this is now generalized, and the Kalman gain is now KK plus 1, because it's done at the instance KK plus 1. And then this is the difference between y, remember y minus something, so zk plus 1 is very general now, minus the old estimate. And then this is because we have combined the measurement with the earlier result, that is xk hat. You know, hat means estimate. You know that little hat? It's called an estimate. So the old estimate is updated to the new estimate by first calculating the Kalman gain, putting the Kalman gain here, and then the current measurement minus the old estimate, and then you also have to update. So one thing very important to remember, and that's this one. The measurement update. See, the steps update is happening over time.
Yeah.
The measurement update is happening bang when I get a GPS reading, right?
Yeah.
So K plus 1 and K are exactly at the same instant. So it's not saying it's a different time. It's saying the new Bayes estimate is obtained from the old one. Both of them are at the same time.
Yes.
You got to remember that. The only time advances is the steps. The steps, your time is changing. Then, bang, you're doing so this is the bang part of it. K plus 1 and K are exactly at the same time. K plus 1 is a new estimate, but at the same time. So the only reason we use K and K plus 1 is because we want to differentiate between the pre and post measurement. The post measurement is happening instantly, but just before we had the result of odometry, right? But now we have to update it, but at one instant. So K plus 1 and K, it's just before and after the Bayes estimate. That's what it means. Is that clear? So that notation is very important. All of this is happening at K actually, or K plus 1. They are the same instant. So the dynamics part, we have not come up with any equations, because this one was just to show you the concept, right? I haven't done any dynamics here. So what are the equations in going from here to here? Now that has to be based on a specific application. Are you using odometry, right? Or IMU? It cannot be problem independent. The perception update, more or less, you can show the concept by equations. But how you move is different based on, what is your problem that you're tackling. So those equations need to be done differently. So, okay, now, so this is stepping back a little bit, not losing the reason why we are doing this. So this is an excellent loop that characterizes robot motion. So where do you want to start? Let's say we want to start here. So right now I have an optimal estimate because I've just done a Kalman filtering. I have the best possible estimate of the state, right? So that goes in here, but you also have a mission. So you're here, but you want to go somewhere else, right? So without knowing where you are kind of precisely, how will you say what are the new driving decisions? You won't start steering unless you know which direction, right? So you figure out where you are and then you make a driving decision, which is V and omega. You give a V and omega to the robot and then it starts to drive, which means the system is going to change its state, right? So the system changes its state, but the system model is not perfect. Therefore, to represent that, you put a system error input there. It means that if you knew that system error, you would perfectly know what the output is, right? Because you know this, you know the system error, so you got this. But I told you, the system error is a number drawn from a probability distribution. So you couldn't possibly know that. It's as you draw more and more, you get different numbers. So when you draw a sample, it's telling you something about the sample, right? But it's not meant to be taken like a precise number. So the reason that you don't have a perfect model is covered by putting a Gaussian there. The fact that you can never ever define the system's behavior perfectly. It's only models, right? So therefore, the system state here is something that you don't know yet because of this, So you don't know that, but you can't do something about it unless you first sharpen your understanding of it. So then you throw in a measuring instrument like a GPS device, right? And that has a measurement error. But the output technically should give you a better understanding of the system state. That's why you throw in a GPS measurement or whatever other kind of measurement. So the Kalman filter, once the measuring device gives its observed measurements, I put it together using Bayes' rule and I do the same thing over and over again. So a driving decision, some state, I don't know what it is, maybe it's inaccurate because I'm counting steps. I use the measuring device, I get a better estimate, and then I do the same thing over again. So that's what you're doing in robotics. And now, finally, let's go to dynamics. So, here is a model. dx by dt is equal to u, right? Forget the w for now. In physics, we have seen this. So this robot is expected to move at a constant velocity down the line. There are many reasons why it can't do that. If it started from rest, how does it get to u immediately? It can't. So there's going to be an initial period where it accelerates, right? So immediately this model cannot be true, right? Let me give you the other reasons. We don't know what the exact velocity is, that's a measurement, right? And measuring is imperfect, right? Okay, you know the controller, how it works? Like cruise control. If you go on an upslope, the speed will initially drop. Then the controller will kick in. It takes time. So the speed will drop and the controller will kick it back up again, right? So how do you get average velocity of constant? You don't. Because you have this up and down, right? Based on the road you're traveling in. So if you go into a little hole, the speed is going to drop temporarily and then it's going to pick it up. Okay, now, I told you this already, noise and velocity measurement. Did you know this? That if the wind picks up, your speed will drop. Even for cars, right? If the wind suddenly picks up and it's directly against you or behind you, the speed will either decrease or increase. So how could you use this model and therefore you throw that in? Because this model is only an approximation, you throw in a Gaussian distribution whose sample is W. So W is not a precise number. W is a sample from a Gaussian distribution. So that makes it an imperfect model. That's what you are seeing right here. See here? Now, computers don't do continuous. D by dt is a continuous operation, right? So the equivalent of that is this digital implementation. Now you may wonder, hey, what happened to the W? I'll tell you in a second. So this is a digital implementation. So estimate, I keep pressing. The estimate at K prime, now you're saying, okay, where did this K prime come from? It's unfortunate. Different books use different symbols, right? And in engineering, we have this constant problem, we have to deal with it. So X, the estimate at K prime. So remember earlier we used K plus 1 and K, and it was confusing. Instead of that, he's saying odometry takes the vehicle, the robot, from K to K prime, right? So that is the steps update. The reason he doesn't want to call this xk plus 1 is because you still haven't done the Bayesian estimate. So K prime is the same instant as K plus 1. Is that clear? You've counted the steps. K prime, you're waiting for a measurement, a GPS, right? But the time is the same as K plus 1. Is that okay?
Yeah.
So there is a time difference between K prime and K. There is no time difference between K prime and K plus 1. So it's just a change in notation. So how come the W went away? Look at this. I'm saying estimate.
Yeah.
If I was saying this was a real thing, then you need to put the noise term in, right?
Yeah.
I'm saying already it's an estimate. I'm imperfect.
Yeah.
So then you can't put the W in because that's like confusing the situation. I'm saying it's an estimate. So over there, I'm not saying that. I'm saying precisely dx dt is u plus w. Here I'm saying it is an estimate, so you don't need the noise. It will be actually wrong to put the noise in there. So this is a discrete form that a digital computer will implement. So K prime is the end time of the action update, the counting steps phase. It is the same instant of time as K plus 1, but used to convey that the perception update operates on the result of the action update. Okay, so the same figures. So you know what odometry is going to do? Well, this can be formally derived because you have that type of an equation. It can be shown that if this is a Gaussian and if you already had uncertainty about its original position, then the uncertainty at the new position is going to be the old uncertainty. Let's look at this. The variance of the noise multiplied by Tk plus 1 minus Tk. As the difference between Tk plus 1 and Tk grows, you're going to get that, going to this, going to this. See, this is adding on to this variance, right? So doesn't that convey to you that I'm losing certainty about my position?
Yeah.
So this is the equation. It can be derived. That essentially what we described earlier, like du by dt is equal to u plus w. Because of the assumption of the Gaussians, you can show that the original variance is getting added on to by this, which is getting bigger and bigger the more time you allow to elapse. And so that is becoming this, which is becoming this. And the point is, you will soon get lost. Because if that Gaussian lays down, it's basically saying, I'm not very sure, I think it could be here, 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 and it's saying I could be anywhere here, and that's getting wider and wider and wider. So it's time for a measurement update, and that part we already covered. Right?
Yeah.
Remember that? We covered that. We need one of these.
Yeah.
Because otherwise he's flattening out, you see? It's flattening, flattening, flattening. He's only shown you after it's kind of flat, but you need a measurement update to shorten the result. And this is the process of flattening. So this is step counting, more and more uncertainty as you go further. So I put back the perception update, now it's complete. So 3 equations, got it? Oh, the ordering is misleading because you first have to calculate this. But that's obvious, right? I say where. So this is done first, then that, then you update the variance. So 2 plus 3, 5 equations. All Calvin filtering implementations have 5. Whether it's matrix, 6 elements in the state vector, anything, doesn't matter. There's 5 equations. Classic 5, 2 plus 3. So the Kalman filter is a mathematical formulation for producing an optimal estimate of the system state based on the knowledge of the system and its uncertainty. And the measuring device, a description of the system noise, that's what it is, uncertainty of the system. The measurement errors, uncertainty of the measuring device. And the uncertainty, the dynamics, that was the W. So 3 Gaussians, right? If you assume you know the 3 Gaussians, you can produce a good result with the 5 equations. Okay, now it's time to get into, I'm going to briefly show you this, but it's more than one element, so it involves matrices. I'm just going to show you that, it can get a little bit complicated. But first we're going to start with this Akshay Chawla. So if you have a MATLAB up and running, you can pull down that KF underscore MK, because I modified his program, so I extended the name by putting underscore MK Mohan Krishnan. So you can pull that down. And also there is another document that explains the setup, the whole setup. So pull that up. If you want me to show you our teams, I can. Here it is. It's in the KF MATLAB example folder. Oh, there's just the KFMK, but not the other document. What happened? Maybe I put it as a parent. So nice pictures. I found out he copied it from another paper without providing attribution, which is a big deal in the West. You can have your career destroyed if you produce a figure from someone else's work without referring to it. And all these figures are not Chawla's, it's got it from another paper. And so I added the guy. So rail cars, I made the rail car instead of a car. A rail car starts to move on a straight track from its starting position, eventually attaining a constant velocity u. See, eventually, it can't immediately get to u, meters per second. In practice, it takes a finite amount of time to reach the target velocity because of dynamics, right? So nice picture. We have an estimate of the initial state of the car. In general, this is a state vector x with a collection of variables of interest, pose, velocities, etc. In the simplified example, it is just the 1D position of the car. So, from this point on, we treat the state vector as containing just one element. For the general n-dimensional state vector, matrices will be involved in the KF formulation. Also, a single variance. Now, I don't know how far to go into this, maybe I won't go into it too much, but when you have a vector which contains a stack of variables, there's only a variance for each one of them, right? But there's more than that. There is the covariance between pairs of them. So the variance, a single term in the one-dimensional case, gets replaced by a covariance matrix. So if you have n elements, let's say 3D position 3, right? X, Y, and theta. You have a 3 by 3 covariance matrix. That's why when you're first studying this, you want to pull your hair out, which I can't because I already lost my hand. But you want to do that because matrices and then derivative calculus with matrices and so on. So it's not an easy thing to explain why the covariance comes in addition to the variance. But we are doing the 1D problem, so this is just a note to remind readers that the actual multi-dimensional case is a little bit more complicated. So we will not cover the general ND KF formulation in this discussion. However, KF is still a 5-step process, the 5 equations. Okay, now the position is going to deteriorate rapidly, like counting steps. So every once in a while, maybe we point a LiDAR gun at the wall and get a measurement. It's a noisy measurement, and for some reason, I can't do it constantly, because if I could do it constantly, I'll say forget the odometry. I'm going to just use my, frequent GPS reading, right? Why would I use step counting if I can look around all the time? So let's assume that the LiDAR gun cannot be used frequently. There is something preventing you from doing that. In practice, the measurements itself could be a vector of measurements. So you can the state can be multiple elements. The covariance matrix now gets involved, but the vector of measurements can be many different measurements. It could be a LiDAR. For SLAM, you have many measurements, right? Because you've been tracking these barrels, and all of a sudden the barrels which were there are here, and you have new barrels. So many measurements. So it has to be formulated in a matrix sense. Otherwise, it will be very confusing. You can't do the n-dimensional case without doing the one-dimensional case first. So the LiDAR device intermittently measures the position of the car by bouncing rays off a ball located at starting position. Once every sample, and that is up to you, whatever it is. Maybe it's once every 10 seconds, right? Okay, we want to formulate a state estimator based on cabin filtering. For this, we need the following. System of process model, there it is. Same thing. With Gaussian noise, so we know the mean and standard deviation of this, or mean and variance. So system noise example drawn from a zero mean Gaussian distribution. Drawn from, this is a sample. This is not a precise number. Next, you call it again, it's going to give you a different number. From this distribution. It accounts for model uncertainty due to not knowing the actual velocity. I copied the previous thing. Noise and velocity measurement, disturbances such as wind gusts. All of those factors and maybe more that we're not thinking of. Since W is drawn from a probability distribution, the position of the robot can only be estimated inexactly like this. You see? That's why you don't put a W here. I'm saying this is an estimate. You remember this equation? So this was a steps update. And then now we have a sensor model. We don't call it Y now, we call it Z. H star, assume H is 1, right? We don't want to complicate it. Sometimes the measurement is not directly in the same domain as the state. Because not all states can be directly measured. You have to measure them indirectly. So then you need some constants here to make the state into a measurement. So assume H is 1, we don't really care here. So assume that Z is X nu plus V, some noise. So 2 noises so far. W, there's one more, the initial position, right?
Yeah.
We had some uncertainty. So 3 Gaussians, so we have 3 means and 3 variances. So the initial position of the rail car is represented by a normal distribution with the appropriate mean and variance. Covariance is the general case, because I want to remind the students, don't relax too much because the real world is a bit tougher with vectors and covariance matrices and so on. So it's not as easy as these equations make it sound. So we assume that this initial position is available to us. So that initial position is used only once, but then you'll move its variance, right, and its mean constantly forward through the system equation, right? So the initial position is only once. After that, it's going to be pushed ahead by the counting of steps, and then you'll update it using Bayes theorem. Then you push ahead with the counting of steps. So 3 Gaussians in total. It's starting to move now. Counting, let's count the steps. So see what happens? That, we saw this earlier. A narrow, tall Gaussian becomes a fatter, shorter Gaussian. And if we don't do something, we're going to be lost. So the variance of the initial estimate, so when you go from here to here, this is, the variance equation I showed you earlier, where the time interval multiplying the variance of the system noise adds on to the position. So that's what we're talking about here. The variance of the initial estimate needs to be correspondingly updated.
Yeah.
Oh, there it is. I was going to go back, but I copied the equation. So it's going to get worse and worse, and that's what you're seeing here. If you compare these two, it's happening because of this equation. So you must not allow the Gaussian to collapse. And we're going to save it by taking a measurement before it collapses. There's the measurement. See, this is good. Because this Gaussian should be taller than that, not the other way around, like is shown in that book. So we need this to be taller than that. We haven't corrected yet. We're just seeing them side by side, right? So this is the K minus. Do you get it? The K minus?
Yeah.
This is the K minus instant. We've got the measurement, we haven't done anything with it. So that's why you call it K minus 1. It'll become K plus 1. So here it is. I calculate the Kalman gain. I update. I copied the same equation, so no new notation here. And because I've combined the measurement with the old estimate, the steps output, I need to update the variance also. So this is the variance update. And that's it. I end up with the green. What do we have over here? Blue and reddish. So now this is the base. Such a simple thing, but it works. So long as you don't lose. Okay, now this we actually got, so this is the result. Let's go to the MATLAB program and run it ourselves. So I'm going to fire up MATLAB. So yeah, because I modified it, I made a note to myself that I did an engine. Let me show you some important things. He's trying to say that this is how you generate a Gaussian random variable from MATLAB. It's random. This is the variance of the original estimate, right? He's using comments. He's saying it's 10 times 10. Which means that 10 is the standard deviation, 10 squared is the variance, right? So 100 is the variance. So here, U is 2.
Yeah.
The spacing between update intervals is 1 second. He's just simplifying it. You can make it 1/10 of a second if you like and rerun. But he's assuming there's a 1 second spacing between, LiDAR readings. Okay, so this is the process noise covariance matrix. You know the W? The W comes from the Gaussian process whose variance is 100, standard deviation 10 times 10. And here's the measurement noise covariance matrix. So R is actually 4 times 4. So maybe I should put here 4 times 4. Because R is doing for the measurement what Q is doing for the process noise. So it's just a coincidence that Q and P happen to be the same. You can play with it. Once you have the program, you can do anything you want. It just so happens that he's chosen P to be 10 times 10 and the process noise. So this is the initial state uncertainty and this is the process noise uncertainty. Happens to be the same here, it does not have to be. Measurement is 4 times 4. And what is the initial state? Here it is, 0. And then you'll find that he's done some MATLAB type of things. He's pre-allocating variables. In one of the earlier programs, I was appending. Remember, I created X and Y and then kept on making it bigger for the robot going around a triangle program. That's not considered good practice in MATLAB because they know it slows down the system. Every time you extend a variable, it has to do some memory calculations. It has to do some address and right? Because when you add something, maybe it's already, the space next to it is already used up. So that continues. See, this memory spot here continues the same array. So that requires some housekeeping. And he's saying, don't do it because it slows you down. So if you pre-allocate it, everything is done. But of course, you have to be sure that 100 positions is enough. Because otherwise you'll overflow, right? So you have to be sure that 100 positions is enough. So some housekeeping. And then he basically runs it from 1 to 100 seconds. You see the same equation. See it? This is the same equation. Yeah. Okay, so the 5 Kalman filtering equations are being rammed through, and he's plotting 4 things. So one is just the title, and then the first one here, XX, is the ground truth. Now, what he calls the ground truth is your basic step counting equation. He's calling that the ground truth. Now, I would not use the word ground truth because ground truth means that reality, his ground truth is actually XX, which is if you just use U plus the noise, that's what he's calling ground truth. That is the horrible model. So if we call it ground truth, it looks like it's the word of God, right? So I think he's carelessly using the word ground truth. I should really relabel that. Now, this makes sense. This is the base output result. So this is the corrected lookup result. So this is the lookup result, corrected state. And then the third one is the predicted state. And the last one is the sensor measurement itself. So I go up here and run it. And the plot sometimes pops up here. It does. And we will look at it. So colors tend to fade out on this projector. But let's see what's going on here. So ground truth is actually the step counting. So that's the blue. The corrected is the orange or deep red. What color is that? Yellow is the predicted state. That is after the lookup, and the sensor measurements are this type of state. And you can see the tracking, right? You can see the Kalman filtering is So if you didn't do that, if you just depended on counting steps, you would have a problem. So a very simple program, he could have done a better job of documenting it. So I'm in the process of cleaning it up because properly cleaned, it's a very good learning tool. So now you can change the process noise, measurement noise, the noise of the estimate of the system, and get the results. You cannot possibly sit down and calculate these things because you get tired, right? So that's the beauty of a program. Now we can change the parameters and see what the results are. So, any questions on this? This is basically a straight implementation of the dynamics of a moving car, which is supposed to be going at constant speed. Now, I am going to show you the other example, the two-dimensional example, because it's worth it looking at it. And that is the Python example. So I have to go back to the PowerPoint. So this is a multi-dimensional case. Now I, at some point, was able to run this Python program. I think I've lost it somewhere between computers, but it's a Python program that I had to do a few fixes and I was able to get it to work. So, quite complicated. What is the problem? It's giving us some theory. I need to know Now, the 7 equations are not the 7 equations, okay? It's still 5 equations. He's breaking up some of them into an extra equation.
Oh.
So Kalman filtering is not 7 equations, he's doing some intermediate steps to make it 7 equations.
Oh.
So this is the code in Python. Oh, this is a voltage measurement. Okay? No. This is that's one example. Voltage measurement, which is like resistor measurement.
Yeah.
Measuring the voltage of a battery is like measuring the resistor of a resistor, right? It's only a static case, so not very interesting. Here it is. We'll use a common physics problem with a twist. This example will involve firing a ball from a cannon at a 45-degree angle at a muzzle velocity of 100 units per second. However, we'll also have a camera that will record the ball's position on the side every second. So that's your perception update. You have a model for the fired cannonball, but you also have a camera like a GPS or whatever you want to call it. The positions measured from the camera have a significant measurement error. We also have precise detectors in the ball that give the X and Y velocity every second. So he comes up with the equations. These are standard equations that it might not be obvious at first glance, but these are standard physics equations. It's a noise because the physics equation is just a model. And on that basis, he generates the problem in matrix terms and then puts it into the program. So by the way, in general, the Kalman filtering is cast as a matrix thing. The old state is multiplied by A, and the input, input is, your velocity input is multiplied by B. And what you have to do is specify the A and B matrices. That makes it very regular. They don't do it like we did for the one-dimensional case, but they have to institutionalize it, mechanize it. And so they cast the new prediction as A times xn plus B un. So this is the step counting thing. And the measurement is coming shortly. So I don't want to spend too much time, but here's the result. I am able to generate this. I was able to generate it with my Python program. I don't know where it is right now, this Kalman 2. It's downloadable from the internet. But I had made some changes and I seem to have misplaced it. But here it is. So look at the Kalman. For some reason, initially, right? Not for some reason. He deliberately uses an initial estimate that is way off. So it starts from somewhere here, right? Look at it. It's running to catch up because the Kalman was fooled by a wild initial estimate, and then it's caught up very quickly, and then it tracks closely. So the measurement is all over the place. So in this case, the measurement is quite bad. But together with the original model, he's able to. This is a rare case where the measurement is bad. Typically the measurement improves things. Here the measurement is bad, and he's able to track it. So this is what happens in all the Kalman filtering applications. The Kalman filtered result gives you the best measurement given two imperfect processes. It gives you the best possible result.
Then why is Markov used?
Huh?
Then why do we use Markov pattern?
Why do we use Markov?
Markov.
Oh, so in Kalman, right, you maintain that one position, but if you're uncertain whether you're going to be able to hold it, it's better to keep multiple choices alive. That's the only reason.
Because this is very close to the metric. It's very accurate.
Yeah, but again, you can't lose that one estimate. So we'll go to Markov. Now that you mentioned Markov, that's because I told you we'll briefly talk about it. So this link, you can go and play with it. Some of you will be better at Python than I am, because I'm basically a MATLAB person. But you can go take a look. So at first glance, you say, hey, that looks like the same figure. We don't know where we are initially. Unlike the Kalman, where the initial position was given, right? We had a similar figure, but we had one bump here, right? Here we don't know where we are. Therefore, we assume a uniform probability over the entire length that we expect the robot to be. So there is some expectation that it can't be beyond 100 meters, let's say. So this uniform distribution only extends from 0 to 100 meters. Let me ask you this, what is the area under this? 1, because the robot has to be somewhere, right? We don't know, and there's no bias, so we say flat, right? We don't have any other information to say it's more likely to be at 50 or 45, so we just give it a flat distribution. So, I think we start with the measurement, so the robot is right next to this pillar. We start with the measurement, so there are 3 of them, right? Because you don't know where you are. So, you look at the map and say, where do I have a pillar? I could have a pillar here, or a pillar here, or a pillar here. That's the difference here, got it?
Yeah.
Because you had no idea where you were. So now when you saw a pillar, you said, oh, there are 3 pillars in this map. I could be here, here, or here. Okay. What's the area under this curve? Has to be 1 still. It still has to be 1. Because if it goes up here, it has to come down in other places, right? It has to be 1. That's the idea of a probability density function. Then, time to do a base upstate, which means look up update, right? So I multiply these 2 together, right? I can't just multiply 2 probability density functions. I have to find the area underneath it and normalize it to 1, right? So that's what this is, right? After normalization, it's after normalization, meaning I find the area and divide. Remember, we had to do that? Because the denominator, we don't know the denominator. This is an indirect way of finding the denominator. Okay, then, so A and B is this figure of normalization. So robot moves right? Look at what happens. All 3. So basically what we're saying is, I could be here, I could be here, or I could be here. But now as I move to the right, it's getting less certain, right? This bump in moving to this new location has become shorter and fatter, got it? Same thing here, same thing here. What's the area under this curve? Still 1. Now you better do something, because all 3 Gaussians are going to get, Markov has multiple positions, right? But all of them are getting wiped out. So, I take a measurement, right? I could be here, I could be here, I could be here. There are 3 pillars. But now, I repeat the process. C into D, just like A into B. Look what happens. It's sharper, right?
Yeah.
But you're not going to kill those. See, there are some bumps here also now because of that. See, that times this created a little bump here. This times a flat created a little bump here.
Yeah.
You're going to maintain all these positions, right? But you're kind of confident that this is where the robot is, but you're going to keep all those positions open and you're going to carry them. So that's the difference with Markov. It keeps all those other possibilities alive. That's the only difference. But it has figured out where it is. And there's a very nice example which you won't go through. It's actually quite an intricate example. It seems simple, but you have to really focus. So we're not going to do that right now. So why don't we take a break at this point, and then I think we should move on to cognition, the last topic. We'll make some progress and then we'll let you go a little bit early because we wanted to have fun. So after the break, we'll start on cognition. I think so. I'm going to check my list to make sure I covered everything. Yeah, all the documents. Yeah. So we have to first realize that cognition is kind of an endless topic, because you can throw in like face recognition, right? But that's not specific to robotics, right? There's no point in talking about face recognition because certainly it's a good example of cognition, probably a very good example, but why is it particular to robotics? So we want to use topics that are particular to robotics. So eventually we settle on the path planning, because every robot that moves has to do path planning, right?
So if it's any question, then why they call recognition? Why not just call it cognition?
No, this cognition is not meant for the face recognition. Cognition is any high-level activity involving the brain. So I'm just saying that face recognition would fall under the cognition. So cognition is all the brainy things that we do, right? As human beings. Even animals are quite smart in some things. So this is like trying to make the robot, the computer in the robot, act like a human being or animal. So it's used in that sense. But let me tell you this: if you put a camera on a robot and say, "Go find the student," he's missing class, then that becomes robotic cognition. That was my point. But it would be so specific that not worth discussing, right? Because you want an example that is very general. Path planning is definitely general. Because every robot that moves has to do a path plan. So that's why in the third bullet I say path and motion planning is an ability which almost all mobile robots need. And by the way, the other branch of robotics, moving arms, they also need motion planning. Because if I'm going to pick up this, if this is here, right, and I'm going to pick it up, that's path planning, right? Because the tip has to move in a certain way. If I move like this, I'm going to hit this. So that also involves path planning. Okay, so wall following is a good cognition technique. So picture the Great Wall of China, but we do wall following all the time. So when we're going down the hallway, the human being doesn't need to say, "Oh, I'm doing wall following," right? So let me look at the wall. We kind of do it automatically. We see doors. Let's say we have a bunch of professors' offices here, right? And we're looking for a particular one. Every once in a while we look up and try to read the nameplate, So it's wall following, but you're also trying to figure out where you are because you have a map in your head. You're looking for a particular professor, right? And then you stop when you find that door. So wall following is a technique that we use when you walk on the sidewalk here, right? When I keep the car within lane lines, that's wall following, right? There's no wall, but you can almost imagine a wall where the lane lines are. So you are in fact, doing wall following. So in structured environments you can do this. If you go to the forest, there are no walls. If you go in the desert, no walls, right? But wall following can only be done in structured environments, meaning that where a human being has built it. Okay, yeah, maze. So you know what a maze is, right? So the idea in a maze is that somebody takes you to the entrance and then you're supposed to find your way through this. You don't have a map. If you had a map, it would be easy. But you don't have a map, so I think the best way is to use wall following. So if you go on the internet, you'll find some of the most common wall following strategies. I think one of them is always find the right. So don't go right left, because then you might be going in a circle. It's always right. What happens when you reach a dead end? Come back and go right again. Wherever you can, again go right in a different branch. But essentially you go right, and you can explore the whole thing. So
and you say maybe circular, like 4 rights is same thing.
well, because you won't get that kind of 4 rights here. If I can put my finger on the exact algorithm, I'll try to find it tonight. But essentially, they say take the right opening and the right opening unless there is a dead end, and then come back and take the right opening again. I think it's called. There's a name for that algorithm. I'll let you know tomorrow. So I took Professor Abraham's advice and updated these 2 videos, and I hope that this version of the PowerPoint has that. So, since you're so excited, I'm going to show the video first, and then I'll create the copy and put it on Teams. Okay? So I'm just giving you a short clip here to excite you. Watch the whole thing. (2023). Are you happy, Professor Abraham?
Yeah. What is the fan? Yeah, see that is a fan
Yeah.
that produces the downforce to make sure that the rod doesn't slip.
Oh, I see.
Yeah.
Now this seems to be like there is room for it to turn gently. Not up, it doesn't have to be abrupt. See, it's curving sometimes here.
It's drifting.
Yeah. Is that the same robot?
Yeah.
So initially it was mapping.
No, that is a slow down version.
Okay. So typically they give you 2 runs or maybe more than 2. There are mapping runs. So you do the same right, which I was telling you about, and you figure out the maze. Then they want to test how good your mapping is. So they take you back to the start, and then because you know the map, you find the direct path, to the goal. So that's path planning. So the first one is to create the map. The second one is to find the best path there. So let's watch the other one, and then I'll refresh the file.
Search out for the known and get to the end of the maze as fast as possible.
Person became second.
Slowly, come on. Stop.
This tiny robot mouse can finish this maze in just 6 seconds.
Oh my God. 6
Every
seconds.
year around the world, people compete in the oldest robotics race. The goal is simple. Get to the end of the maze as fast as possible.
Person became second. Lost in 20 milliseconds.
But competition has grown fierce. When somebody saw my design and said, "You're crazy!" Why is there so much tension? What's wrong anyway?
All that.
This video was sponsored by Onshape. In 1952, mathematician Claude Shannon constructed an electronic mouse named the...
So this guy went to the University of Michigan, which is about 25 miles from where I live. We do miles in US too, so you can figure out the kilometers. So they have a tribute to him inside the electrical engineering department. They have a picture of him, and he's also a computer guy. He built one of the earliest computers. So that old computer from maybe the 60s is behind a glass panel. I have a picture of it somewhere. If I can find it, I'll show you tomorrow. But that's Claude Shannon. He got his master's, I think, at the University of Michigan. He's a Michigan. Michigan is a state, so he was born there. So he's like a big hero in Michigan because of what he achieved.
species that could solve a maze. The trick to making the mouse intelligent was hidden in a computer built into the maze itself, made of telephone relay switches. The mouse was just a magnet on wheels, essentially, following an electromagnet controlled by the position of the relay switches.
He is now exploring the maze using a rather involved strategy of trial and error. As he finds the correct path, he registers the information in his memory. Later, I can put him down in any part of the maze that he's already explored, and he'll be able to go directly to the goal without making a single false turn.
Theseus is often referred to as one of the first examples of machine learning. The director at Google recently said that it inspired the whole field. 25 years later, editors at the Institute of Electrical and Electronics Engineers, or IEEE, caught wind of a contest for electronic mice, or Le Mouse Electronique, as they had heard. They were ecstatic. Were these the successors to Theseus? But something had been lost in translation. These mice were just batteries in cases, not robots capable of intelligent behavior. But the misunderstanding stuck with them, and they wondered, why couldn't we hold that competition ourselves? In 1977, the announcement for IEEE's Amazing Micro Mouse Maze Contest attracted over 6,000 entrants. But the number of successful competitors dwindled rapidly. Eventually, just 15 entrants reached the finals in 1979. But by this point, the contest had garnered enough public interest to be broadcast nationwide on the evening news. And just like the rumor that inspired the competition, Micromouse began to spread across the world.
Grammarly now uses AI to help you write, not just revise. Type a prompt and generate a
まず昨年のこの大会で全日本マイクロマウス大会のハーフサイズ競技部門で優勝してまして、 去年作ったロボットからさらにブラッシュアップして作ってきたロボットで今年も連覇になっていこうと思っています。
Even people in the top 2 or 3, you can see them trying to set their mice up and they can barely find the buttons to press because it's absolutely nerve-wracking. It doesn't matter what it was, it could be horse racing, it could be motor racing, it could be mouse racing. If you have a shred of competitiveness in it, you want to win with it.
Just like a real mouse, a micromouse has to be fully autonomous. No internet connection, no GPS or remote control, and no nudging it to help it get unstuck. It has to fit all its computing, motors, sensors, and power supply in a frame no longer or wider than 25 centimeters. There isn't a limit on the height of the mouse, but the rules don't allow climbing, flight, or any forms of combustion. So rocket propulsion, for example, is out of the equation. The maze itself is a square about 3 meters on each side, subdivided by walls into corridors only 18 centimeters across. And in 2009, the half-size micromouse category was introduced, with mice smaller than 12.5 centimeters per side and paths just 9 centimeters across. The final layout of the maze is only revealed at the start of each competition, after which competitors are not allowed to change the code in their mice.
小峰さんがおっしゃっていた宇宙人枠とはこのことか。勝利争いは彼のね。
The big 3 competitions, All Japan, Taiwan, and USA's APEC, usually limit the time mice get in the maze to 7 or 10 minutes, and mice are only allowed 5 runs from the start to the goal.
So if you spend a lot of time searching, that's a penalty. Right?
So the strategy for most micromice is to spend their first run carefully learning the maze and looking for the best path to the goal, while not wasting too much time. Then they use their remaining tries to sprint down that path for the fastest runtime possible. Solving a maze may sound simple enough, though it's important to remember that with only a few infrared sensors for eyes, the view from inside the maze is a lot less clear than what we see from above. Still, you can solve a maze with your eyes closed. If you just put one hand along one wall, you will eventually reach the end of most common mazes. And that's exactly what some initial micromouse competitors
You
realized.
saw that? If you put one hand on one wall, you will solve any maze. That's what you meant. That's what I was saying. Which is, right. So, all right. So you can watch the rest of it on your own. So I'm going to just create a PDF again and of this new version. And so this competition is not that easy to post because it has a
Sir, but how does it come to know that the maze has ended? When it reaches the center, there should be some different color or something which it says.
It is there. White.
Oh, right.
And it's a white color.
But also,
there is a pole in the center.
but also the time measurement. It has to be very precise.
Right.
2 a second is not enough.
No,
Because it's going down to 3 decimal digits, right?
it has to be.
Okay, so initially I had the wrong one put up. Now this is the right one. So wall following. That's where we got distracted, and we saw a couple of nice videos. You've already seen those. But now, if you want to have enhanced wall following, then if the wall is curving like this, right, curving, then you probably want to also look ahead so that you can start curving. And that's how we drive, right? We don't drive right up to the obstruction and then try to turn. So there are algorithms that have a look ahead capability, and also you must move smoothly. Now you don't see that here because this micro mouse is so light, so it's a kinematic vehicle. But if you have a regular car, then you have to worry about smooth driving also. So move smoothly, avoid static and moving obstacles will introduce another element of difficulty. And let's go to this one. So this one, yeah. So this is a project in Japan. project in Japan. So the concept is this, that in airport, you have these transfers, right? One gate to another. And sometimes these more modern airports, it's like a mile, you have to walk a mile. So if you have elderly people, the idea is that you can't have a human being pushing the wheelchair, which they do now, but how many human beings can you have and what is the cost associated with labor? So they're coming up with this is a test project, autonomous wheelchairs. So apparently the idea is to scan your boarding pass and then it will take you automatically to the next gate.
東京国際空港ターミナル様とパナソニックでは2020年に向けて訪日外国人の方や車椅子で移動される方にとってもより安心で快適な日本の旅を楽しんでいただけるようなサービスの共同実証実験を行っています。こちらはロボット電動車椅子ウィルメックスです。バスや車の到着口で専用アプリから呼ぶと自動的にお迎えに上がりチケットカウンターまで自立移動します。人や障害物にもぶつかることなく走行し、複数台が追従して移動することも可能です。将来的には空港内のさまざまな拠点へ
Differential steer, not skid steer.
乗った人の指示に従って移動できることを想定し、開発を進めています。こちらは交通案内再現し、訪日外国人の方々の日本での一番のお困りごとが移動経路情報の入力になっています。このお困りごとの解決のため、空港から各所への移動経路を日英で表示、さらにはリンク例で5言語の経路案内をご提供しています。こちらの京急成田空港国際線ターミナル駅のチケット売り場では、リンク例スポットライト型を導入。リンク例で目的駅までの移動経路、時刻表を表示することができます。
羽田空港の国際線ターミナルはユニバーサルデザインを
It's not too interesting because you get the idea. So this is very big. So I have a PhD student who's working on creating the best trajectories because this is still slow, right? It's going so slowly, right? Because I guess they don't want to risk hitting somebody. But if you can move the vehicles a little bit faster, then you'll have more throughput, because the point is, the flight is supposed to leave at a certain time. You can't be, sometimes they only have 1 hour connecting time. So there has to be more optimal motion, right? So it has to go a little bit faster. So you have to have a good motion model and you have to be able to go faster and stop faster also. So this is nice, but it's going to be stopped by anybody crossing the path. So let's get back to the PowerPoint. And so I showed you this in the morning. This is the evaluation of the different vacuum cleaners. So that's it's an autonomous lawnmower actually. I'm sorry, a vacuum cleaner. So the autonomous is one aspect of it, but I was more interested in the localization and mapping aspect of it. So this is the basic pseudocode. If robot is too close to the wall, turn left. If robot is too far from the wall, turn right. So I'm assuming that I'm following the right wall. But then the pseudocode has to be translated into more precise statements, which are computer code. And that's where the challenge begins. So this slide basically points out that you can't demand the best, costliest sensor in the world, because you're always going to be limited by the project budget. So therefore, the answer is not just to say, give me the most costly sensor that you have. You have to manage with the best sensor for the application. So that's why, yes, the sensor plays a major role, because if the data coming in is flawed, then you have to do more work writing code in order to get the result you want. But the practical aspect is that you have to work with the costs. Okay, now what is path planning? So a vehicle typically has to move from one location to another, right? A current location to a destination. And it needs to do that through an environment that is partially known or completely unknown. Notice, I don't say fully known. The fully known category is excluded because there's no such thing. There's no such situation in the real world where you fully know the map. There's always going to be some changes in the map, people walking across, etc., etc. So it's either partially known or completely unknown. So then this bullet distinguishes between these two words, path planning versus navigation, or equivalently trajectory planning. So here's the difference. So the typical paths that a path planner spits out is made up of straight lines connected at sharp corners. So you draw a line like this through the obstacles, right? But a vehicle cannot, like just because you draw a line like this doesn't mean that the vehicle can go through that curve. Because think of these big trucks. So for a big truck, this means something else than a bike or a Volkswagen. So therefore, the path doesn't have any time information. The trajectory planner has to provide x, y as a function of time t. The path is just x, y, independent of time. The trajectory planner has to give x, y, t. In other words, that x, y, t is a trajectory that is drivable for the robot. That's the difference. That's why trajectory planning is more difficult, because you have to figure out the dynamics and kinematics of the robot, how it fits in. So it takes into account the kinodynamics. So kinodynamic is a combination of kinematics and dynamics of the vehicle and driving the vehicle along the planned path. It is a time-based schedule. So path planning is up here, trajectory planning is down here. Now, this has been done in academic research. Why not combine the two and solve it as one problem? The moment you do that, the moment you combine path planning and trajectory planning, it becomes a more difficult problem to solve. So that's why they do path planning separate, and they're willing to accept these kind of results. Like straight lines joining at odd angles. In fact, when you get a Google Map directions, right, that's exactly what it's telling you. It's saying go to this light, turn right. So it's like joined by straight lines. Now, it so happens that in the US and in Canada, that all the roads are laid out this way. North, south and east, west. So the turns are not angles, but they are like right angles, always. So that's what Google Map tells you. It says take this route. But the car, to figure out what is the fastest way to go through that, it's a different story, right? You have to slow down, but you don't slow down and stop unless there's a signal light. You try to go through the curve. How fast can you go, right? So that's the question of optimality. So also the path planning is carried out on the basis of gap analysis. And you know what gap analysis is? It says, is there enough space between these two obstacles in order to fit the vehicle? But fit what vehicle? Well, that's the thing. A huge truck may fit, but fit is not the same thing. If I fit here and fit here, doesn't mean I can drive through this. You know what I'm saying? Maybe I fit here, and then you're asking me to go this way. Okay, I fit here, but can I drive from this position to that position? That's a different question. Path planning does not consider that. They say it's up to you. So often you end up by generating a path, and then you find the vehicle cannot follow it. So even if the vehicle stops and backs up, it's not possible. So that's why you need a control system. So a control system is needed to abandon the path, right? Because you're going to try and slow down and go through that, but if you can't, then at that point you have to ask for a new path. So often you have to replan. So in general, a robot has to, so by the way, the path plan which I said is at right angles, that's for roadway driving on a road. There are two types of driving modes. One is driving on the road, right? Which is the more difficult one. The other one is open field. We call it open field navigation. So in the battlefield, there are no roads, right? So then it's called open field navigation. So these two have their own challenges. Roadway driving, you have to identify the edges of the lane. So that requires vision. Open field driving, no need for that, because there are no lane lines. So in general, this makes roadway driving a little bit more difficult. So basically, the robot has to find the goal and avoid the obstacle. It's really quite simple. Obstacle avoidance takes precedence it's more important compared to goal seeking. Because in the interest of getting to the goal, you cannot run over an obstacle. I cannot just go through this obstacle because I want to get there. So I have to go around this. So it's this very simple behavior. When you reach an obstacle, try to avoid it. The moment you avoid it, go back to goal seeking. So it's two behaviors. So obstacle avoidance takes precedence, and then when the obstacle is gone, you raise the goal seeking. Now, wall following is kind of a unique thing because you're avoiding the wall, but you're also using it to find the goal. So wall following is a special case where you're avoiding the wall, but you're also following it. So it's also giving you goal seeking. It's the same thing that is doing both. You avoid it, but you use it to follow the goal. So this is what I was telling you a few seconds earlier. There are two types of motion: open field or point. They also call it point to point. It's like a military vehicle out on the battlefield. And the second type is roadway type. Now the status of the environment, it's only partially known because accidents and congestion updates, depending upon when it occurred, may not have resulted in a map update. And generally, it's not in real time. Even today, it's not in real time. They're getting better at it, but if the accident happened just minutes before you reach the spot, then typically you're going to be stuck there. There's no alternative because they couldn't anticipate it. Other moving vehicles are definitely not on the map, right? So self-driving cars, their maps have it, but human beings, the other moving vehicles is not going to show you on the map. So maybe in the future at some point they'll put it on the map so you can figure out congestions yourself. Because then you'll know that, okay, the next segment of road, there's a lot of vehicles. And you can take the exit and do something else, something different. Now, typically going to the final destination is not just where you are in the final destination. You actually fill in the space in between with interim waypoints. We also use the word breadcrumbs, like an ant follows breadcrumbs, small pieces of food. So waypoints are like go here, 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 here to the ultimate destination. So it's a attempt to show you some intermediate points so that it's not just the final goal, but you also have some intermediate targets. And then you have to deal with emerging situations. The path plan does not tell you all these things. You have to deal with emerging situations based on the local map, like stay within lane, avoid stopped vehicle. Suppose the vehicle stops in front, the path plan is not going to tell you anything. You have to avoid the stopped vehicle on your own. So all of those are local maneuvers. Path plan does not tell you how to locally maneuver. The two things are different. Okay, now here's the objective. Now it's very interesting because you always, when you say, okay, what is my goal? You say, okay, I need to get there as fast as possible. No, that's just one of many possible objectives. Because it can also be the shortest path. I want to get there traveling. You're saying, aren't the two the same? No. Because typically in Western countries, when you take the highway, it's the longest path, but it's also the shortest path in time. Did you know that? Like going on the highways is actually longer because the highways were constructed wherever they could get permission to build. So typically the highway goes like this. Your house could be here, but you can't go like this because you'll have to climb over houses, right? So the highway, it goes wherever they got permission to build it. Whereas if you go to the surface streets, all the surface streets are laid like this. Highways go like this. Surface streets are all, grid. So typically the shortest path is if you go to the streets with lights. But if you have signal lights, you're going to be slower. So that's the trade-off between the two. If you go on the highways, you're very quick, even though you're going further. So most economical, right? So what is most economical? I have a big mountain here, and I have to get to a destination on the other side. Climbing consumes more gas. But maybe I go around the base of the mountain, right? Longer path, but not much gas used. But if I climb, a lot of gas used. So how do I put all of these together? Maybe you want a little bit of safety and a little bit of speed and a little bit of distance. So typically what they do is they come up with one function that you're trying to optimize, and it has multiple terms. So A times the time plus B times distance plus C times, you'll have to figure out how to quantify safety. So it's A times the first quantity plus B times the second quantity plus C times the third quantity. So suppose I make one of them 1 and the other 0, it means I don't care about the others. It's pure speed or pure shortest distance, right? But if I say 40% for speed, right, I'll put a 0.4 there. And then the other two I might say 0.3, 0.3, 30, 30. So that means you're giving equal importance to the other two, but the biggest importance is to the 40. So that's how you optimize an algorithm. You have this linear combination of time, distance, and the safety number. So therefore you need a formal framework to solve this. You can't just look at it and say, okay, I think this is better. You have to have a mathematical framework. So now we come to the bug algorithms, right? So the bug algorithms are the oldest algorithms for path planning. So does somebody use them now? No, not really. But you'll find Python programs, MATLAB programs, C++ programs for the bug algorithms. They'll be all over the internet, different people doing it, because it's so classical that people like to test their abilities to program it. There are two basic bug algorithms, bug 1 and bug 2. They're really inspired by insect behavior. When an insect is going to a destination, when it reaches an obstacle, it will go along the obstacle till it gets to the other side. So that's why they call it the bug algorithms. Now, whether the insects know bug 1 and bug 2, I don't think so. I think they made up the bug 1 and bug 2, but the basic thing is the insect hits the obstacle, it goes around. So it is a common sense approach. Missing a space there. Assuming no map available. So you don't know the map. If you knew the map, your strategy is going to be different. Because you don't know the map, right? You have a different strategy. Okay. Here are the assumptions that you make for this algorithm. That the robot is equipped with a contact or proximity sensor. So it's going to go right up to the wall. It cannot see 10 meters from the wall, right? Because if you could see the wall 10 meters away, then you will start angling away this way, right? Why would you go to the wall and then turn left or right, right? So they assume that the bug has to feel the wall. And therefore it cannot start making a decision when you're 10 meters away. The bug cannot see. It has to touch the wall to know that it can't go through. So bug is considered a point object. So bug has no size. And finally, most importantly, this is the final thing. There's one more before that. The bug can localize perfectly. And we know that's not possible in the real world. So we assume the bug precisely knows where it is. It's able to figure out this distance. So it's able to figure out the distance between its current location and the goal. Always. As it moves, it's able to figure out I'm 10 meters from the goal. So it has that ability. Bugs don't have it. But the robot version of that, it is able to calculate this. So the basic strategy is move in straight line towards goal till we run into obstacle. Then go around obstacle, pick left or right. So it can be either left or right, but since it doesn't have a map, take your pick, right? So you could be wrong by picking right, or you could be right. It's random. And then you continue towards goal. But you will understand this better if you have a picture. And here it is. These are the classic pictures from the original bug document. I don't know when it is, but many years ago, probably 30 years, 40 years ago. So repeat the following. This is pseudocode again. Repeat the following steps till the goal reached or unreachable. You'll see an unreachable case shortly. So start moving in straight line towards goal. See here? It knows the goal is there, so it starts moving. It is reducing the distance, right? If obstacle encountered at hit point, so this is the hit point. At hit point, circle around it till best leave point is determined. Now, this would appear strange to you, but why did it come all the way around again? See, it went around, it didn't continue. It went all the way around again, and then it continues, right? Because there is no way, when you don't have a map, that you will know that this is the best leave point. What if this, let's call it an island, what if this island goes out this way and then comes back? Then the leave point will be here, right?
Yeah.
Best leave point. So it doesn't know that until it does the whole island. Is it clear? Or rock. So it seems stupid, and I'm sure the bugs don't do this, but the only part of the bug algorithm is the bug. After that, humans made up this bug 1 and bug 2 and got a paper out of it probably, if it came from a university. So you go all the way around, and then all the way around, and then when you've done it completely, you realize, okay, this is the best leap point. You don't know that initially. Only on the second pass, you know, okay, that is the best leap point. And then you do the same thing all over again. Now the bug algorithm doesn't say the second time you hit go right. That's, I bet you somebody has done that variation. The first time you hit, you go left. The second time you hit, right here, you go right. There is the version probably on the internet, but here if you pick left, it's left, left, left all the way. So again, you'd say, oh yeah, so close to the goal, why doesn't it take off? No, because this is the bug 1 algorithm. It has to go all the way around, and then it realizes this is the best leap point. Look at this situation. So you can't say, hey, it's obvious, you can't make it. No, it doesn't have a map. It does not have a map. So it can't say, this can't be solved without trying it. So because it doesn't have a map. It doesn't see what we see. We see the whole map, right? It can only see, and it can't even see the wall, because remember, it has to touch the wall. So it can't see anything. So it's a completely different situation. Same thing, they pointed out, the person solving the maze doesn't have a view of it, because otherwise it'd be easy, right? If somebody is high up and say, hey, go right, go left, it'll be so easy to solve the maze, right? That person cannot see any of that. So, but remember, the robot cannot see what we see here, no map, okay? So we need shutdown, meaning that how long are you going to try it? So you have to have some kind of algorithm to say, shut down the robot because there is no solution. Otherwise it's going to go round and round. So you get it why it's, so it goes here, right? And then again it's trying to find the best leap point, so it keeps going. And then when it comes back to that, it should realize that, okay, there is no way, no point in continuing. So bug 2, only difference with bug 1, fixed line between starting point and goal. So this is the fixed line. In the other one it wasn't like that, if you remember. See? They do not focus on this line. Here they do. So it's here, it always is this line. Robot does not completely circle obstacle to determine best leap point. Best leap point is established when robot encounters the anchor line. So this is the anchor line. And so when it reaches this, it says, I don't care. Maybe there's a better, shorter path further on, but I don't care because I have reached that line, anchor line, and so it's going to do a left right again. And this is the failure case for the same, example as earlier. So there is a variation with pseudocode in reference to. But my question, which I ask at this point, is which one is better? And most people say bug 2 is better. It's not true. We'll find out why here. So we're going to watch this video. It's pretty obvious, the example they show you, but you would not think it. You would say bug 2 has to be better. It depends on the obstacle, that's right. It depends on the environment. One could be better than the other, and this is a beautiful example. So bug 1, layout 1, there'll be layout 2, and both bug algorithms will do both layouts. So let's watch. So he's trying to find the best leap point. See, he put a dot there because that's the least. Did you get the idea of the dot? Why the dot is significant? So he puts the shortest, he puts a marker there, right? It can be updated, but it doesn't have to be in this case because that turns out to be the best leap point. See, he put a dot right there, see? And then it can be updated, but there is no opportunity to update it, so he does that. Got it? This is bug 1 or bug 2? I know. This is bug 1. So you saw that? This is critical to understand. So these are the statistics that will tell you whether one is better than the other. See here? Euclidean distance, can you get shorter than the Euclidean distance? Not possible, right? The straight line distance has to be the shortest, 200 units. Actual distance traveled, 546 units. So the ratio, which should be 1 ideally, if there's no obstacles, it will be 1, right? It's 2.7. Bug 1 layout 2.
So how is the Euclidean distance?
What's that?
So how is the Euclidean straight line between the points.
Yeah, it's a straight line
You
distance.
can't move,
So it is
like,
x2.
through
Huh?
You can't move through the obstacle. Right?
No, you can't. What I'm saying is that that is used as the absolute minimum that you can get. If there were no obstacles in the field, then you'd be achieved that, right? So he's using that as a baseline for comparison. Most of the time you can't approach that obviously, because the moment you have an obstacle in the way, you have to go around. But they're using that as like a reference point. So what's that red dot? It will tell you which is the closest leave point. Okay, so that's what it is. It'll update it. That will be updated definitely, because there's one on the inside of that barrier. So far he has not beaten that leave point. So no red dot update. And there he'll update the red dot. Right there, see? Now why does it do that? Right? But that's the algorithm, right? Did you understand why he did not directly take off from here? Because the algorithm says find the best leave point. So he has to go around the whole structure. So that turned out to be the best leave point. 13 times. Alright, come on. Bug 2 layered 1. Take off, yeah. And that's it. See the difference? .01. Right?
Yeah.
The best. Same thing. Why did it do that? Do you know why? Because we have a rule that will go left. So let's go back a little bit and follow that again. So it shot the shortest point on the anchor line, and then it went on the, see, because it reached the anchor line, right? It decided to move towards the goal, but then it hit this structure here, and then what is the rule there? Go left. And now it's going to go crazy, because it's going to say, okay, and then it's going to go this way again. It's building up a lot of distance. A lot. It is ready to leave, but it has to go left to get around the last part. And now it gets it. Let's look at the numbers. 65 it went up to. So the answer is, as somebody said, it really depends on the environment. So there is no obvious answer. Which is more optimal? You might say bug 2, but it really depends on situation 1. So bug 1 is following an exhaustive search form. So this is from computer science. An exhaustive search is, I'm going to try everything, right? That's why it goes all the way around to find the best leave point, right? Bug 2 uses an opportunistic. That means it says when I find the anchor line, I'm going to go. So opportunistic versus exhaustive. So in computer science, you'll find this term greedy also. Greedy, opportunistic is greedy, same thing. Let's say it's a greedy algorithm. That's what you mean. For more cluttered environments, bug 1 will tend to perform better than bug 2. And actually, computer scientists prove this mathematically. In general, these algorithms will find a solution if it exists. If there is a solution, it's going to find it. It won't get stuck. There are other algorithms that even if a solution exists, it may get stuck. So So there is a tangent bug algorithm, the code is somewhere, I found it maybe it's in Siegbart's book or somewhere, but there is a tangent, so that uses a finite range sensor. That means you're allowed to see the wall from a distance and start moving. So, obviously the bugs don't know that. So somebody said, I'm going to create a tangent bug, which means if I see the wall there, I start, trying to go around it. Human beings would do that. Human beings won't go across right up to the wall and then say, let me go along the wall. You'll start, veering off. So that's what this algorithm is. So I spent a few minutes on this because it's so important. Because when I was, young, many years ago, I used to be scared of this word optimal. So when you hear this word optimal algorithm, then you stop searching because you say, okay, the best has been found, I can't do any better. The thing is, that word optimal, italics, really has to be taken along with all the assumptions made for that problem. So optimal is based on the assumptions you make. There's no such thing as optimal, meaning the word of God. It's optimal based on these assumptions. And somebody else could come up with another optimal that is based on their set of assumptions. Right? Also, let's go to the first two bullets. Optimal often means that it's so from a certain perspective based on the assumptions involved. You could have several optimal results. Okay? So, you might not be able to implement the optimal because, yes, it's optimal, but it's so complicated that when you actually implement it, computational cost, maybe it takes 10 minutes, you have to sit and wait for the path plan to be delivered to you. That is a cost also, isn't it? Yes. So optimal in mathematics, in theory, 50 pages, somebody has derived this, doesn't mean that you can implement it like this, so you have to put a cost on the practical implementation. So, computation cost involved in actual real-world implementation might be excessive. That is suboptimal when this is considered. So, there are path planning algorithms where people just do a rough plan, so certainly not optimal, but they get the robot moving. Because if you have to wait 5 minutes for a plan, you're losing time, right? So they get a rough plan and then they start moving. So how is this possible? Maybe you send a drone and that gives you a very rough map, its eyes are very poor. The drone roughly picks out the open areas, right? You're on a battlefield. Enemy artillery shells are being lobbed at you, right? So you start moving because you don't want to be still. As you go, you plan a better path. You know what I mean? Yeah. So as you go, you plan a better path, and that might actually be a more optimal approach than using the optimal approach. So that's why the suboptimal solutions are great. It's a question of can you implement them quickly, and that's what you go for. Also remember, these ideal and optimal solutions, they assume sensors that are perfect, actuators that are perfect, right? But sensors are never perfect. Actuators, I think I may have given you this example, the same command twice might put the robot in a slightly different position. So there's no such thing as perfect sensors or perfect actuators. So those assumptions don't mean anything in the real world because there's no such thing. So you're free to develop your own, suboptimal algorithm. I don't want to throw these optimal algorithms into the trash can because they provide some insight, but one should not be scared away by the use of the word optimal.